So I'm going to tell you about one aspect of my research, which is something I care a lot about, but represents a small part of what we do in my lab in Montreal. Before I start, let me do a few plugs. So the book that I wrote with Ian Goodfellow and Aaron Corville is out. Unfortunately, apparently it's not available yet in India, but I'm making pressure on MIT Press so that they will fix that. But the chapters are also for free online for those who can't wait or want to get it for free. Another plug is that we got a huge grant in Montreal for pushing forward both deep learning and optimization. And we're looking for new professors, researchers, students at all levels, and many companies are opening shop in Montreal to let's say, partake in the big deep learning party that's happening these days. So before I start talking about bridging the gap between neuroscience and deep learning, let me say a few words about deep learning. There's been a pretty amazing series of breakthroughs in applications, starting with speech recognition, computer vision, and more recently several applications involving language. This is an example of the kinds of things we did already 2 years ago, where the computer reads an image and it generates a natural language description, like here it says a woman is throwing a frisbee in the park. And the particular system we developed also uses an attention mechanism where for each word that it's going to generate using a recurrent net, it has the option to put more or less attention in different parts of the image at some high level of representation. This is not at the pixel level. And so, for example, here, just before it says frisbee, it's actually looking at the frisbee. Similarly, when it looks at this image, it says a dog is standing on a hardwood floor, and when it's about to say dog, it's looking at the face of the dog, and so on. Now, I'm going to try to play some demo coming from my colleagues at Facebook, showing similar kinds of abilities. Let's see if this works. So,
is there a baby?
Yes.
What is the man doing?
Typing.
I don't know if you're hearing.
Is the baby sitting on his lap?
Yes.
So the computer is answering questions by looking at the image.
Yes.
Is there a baby in the photo?
Yes.
Where is the baby standing?
Bathroom.
What is the baby doing?
Brushing teeth.
What game is being played?
Soccer.
Yeah, I'm going to stop here. You could go on.
Yes.
What game is the dog playing?
So as you see, we've made a lot of progress since the 80s. I wouldn't completely trust these demos because, companies try to make it look nice, but there really is pretty amazing progress, and it's not going to be the subject of my talk to tell you about everything that has happened over the last decade to bring us here, but one of the aspects that's really important is that we're training these really large neural nets that have millions of parameters, or even hundreds of millions of parameters, and we're training them in a way that optimizes all of the layers, all of the components of the system together with respect to one objective function. And it really is something that makes a big difference. And the reason I'm able to say this is that when we started this first few approaches to deep learning, we were training the layers separately using a local unsupervised procedure. And once you start being able to train all of the layers together, it makes a huge difference. So that really is related to a very fundamental question in machine learning and in neural net research from the beginning of the 80s, which is credit assignment. How do we know what the intermediate layers should be doing with respect to whatever the task is? Whether it's supervised or unsupervised here, it doesn't really matter. We have some kind of global objective to try to fit the data in some way. And how do we send a signal to the intermediate layers so that they can figure out how they should change? So there are, of course, many learning algorithms, and in terms of neural nets, there are essentially three types of methods that people have explored. One is backpropagation. So what I mean here by backpropagation is not the supervised learning, it's not gradient descent, it's just how we compute gradients by the chain rule, essentially. Another approach, of course, is that preceded backpropagation is the approach that's we found in most machines that relies on a kind of stochastic relaxation. And another family of approaches based on ideas coming from reinforcement learning, things like reinforce, for example, which I think ideas that have been popular in neuroscience, but I think are totally hopeless to do the kinds of things we want to do here, where you're trying to correlate small changes at the level of either neurons or synapses with some global reward signal. The problem with that is that if you have a large network, this is just not going to scale because the noise in the signal grows linearly with the number of random sources here, number of neurons or synapses. Okay, so one thing I'm interested in is how would the brain do something like that? And in particular, I'm going to focus on ideas coming from inspiration from backpropagation, but we're going to end up with something that's actually sitting in between both machines and backpropagation and getting properties of both. Sorry about that. That's Microsoft's fault. So mostly my talk is going to be about some forms of biologically plausible versions of backprop. And this thread we started about 2 years ago, starting with this notion of target propagation, and a version of it called different target propagation, which works reasonably well, and with which we were able to train single layer autoencoders. So one input layer, one hidden layer, one reconstruction. Then more recently, about a year and a half ago, we showed that you could reproduce some of the properties of spike timing dependent plasticity, the relationship between the spike timing and the weight change, using a purely rate-based learning rule that only looks at the product of spiking rates and temporal derivatives of spiking rates. Then a little bit later, getting close to the stuff that I'm going to tell you about, we showed that if you have a recurrent net, so let's say it's a layered network where you have both feedforward connections and feedback connections. So together this is a recurrent network that has dynamics. And now if you look at what happens near a fixed point and you introduce a perturbation to the dynamics, that perturbation will propagate throughout the layers, and the initial propagation of that perturbation will essentially compute the same thing as what backprop computes. So this was sort of a starting point to make a connection between dynamics and changes in fixed points and backprop. There's of course a lot of earlier work that's related to these kinds of ideas, in particular from Sebastian Sung. More recently, so the last paper, which is mostly what I'm going to talk about, gives a more complete theory. So it doesn't just tell us what happens in the initial stages of the propagation of these perturbations, but it actually tells us that if we continue the propagation of these perturbations until a new fixed point is reached due to the push that has come from the outside, from say the prediction error, then you have all the information you need to compute the exact gradient with respect to some objective function. I'm going to explain that in more detail. And we also show that, in fact, the kind of update rule that you would want looks like some kind of contrastive Hebbian update that could be implemented by, again, something, the same kind of STDP-like rule, rate-based STDP-like rule that we studied before. So yeah, and one last thing we did recently is trying to deal with an issue with these kinds of networks, which is because they are recurrent nets, they might take some time to reach a fixed point, which is where we need them to be to use these update rules. And that wouldn't be biologically plausible if you need a lot of time before the system can be in a state where learning is meaningful. We would like to be able to learn from, very little computation, where maybe it's just a feedforward path followed by a little bit of relaxation. And so we looked at conditions in the architecture of the network, again, bringing in ideas of layers of autoencoders that would make the feedforward inference approximately discover a fixed point of the dynamic. So you can very quickly find a fixed point if you have the right conditions. Okay, so this was a high-level overview of the things I'm going to tell you about. Hopefully things will become a bit more clear. So we've studied a particular energy function in many of those papers. You could replace that with other energy functions. So the methods we've been looking at are based on the idea that what neurons do, and that's not a new idea, of course, is minimize an energy function. So not how they learn, but how they behave, how they change. So their temporal derivative, so let's say S is the state of the neuron, like the weighted sum of inputs. How it changes over time is going down some gradient, the gradient of an energy function. So in these models, the state is always continuous. You might get spikes by sampling from corresponding distributions associated with those states, but the basic random variable that we're thinking about is continuous valued, and we're thinking that what the brain is trying to do with these kinds of differential equations is do inference. So find an explanation for what it's seeing currently in some context that minimizes the energy. And low energy configurations correspond to higher probability configurations of the model. This is, of course, a very classical idea that you find in Boltzmann machines and Hopfield nets from the early 80s. So if you take this particular energy function and you take the derivative, you find that the direction in which a state moves is essentially a weighted sum of inputs with some kind of gating that prevents the state from changing when the network is saturated in one direction or the other. So yes. Yeah. So S as a vector is a configuration of all the neurons. Si is for the ith neuron. Wij is the weight between neuron I and neuron J, and rho of Si is the firing rate of neuron I. S is a scalar, but it's going to change over time, right? So here I'm looking at a particular time, and here's the temporal derivative at that time. Si is the ith element of S. S is a vector of the activities of all the neurons in the system. Well, Si is a scalar. S is a vector. Okay, so the other thing you can do besides going down the gradient is, in addition going down the gradient, sorry, here is Z instead of S, you can add noise, and then of course you get a Monte Carlo Markov chain, which means that you're not just going to the most probable configuration, or you go down the gradient to probable configuration, you also sample the probable configurations according to a probability distribution that is going to be something like e to the minus energy. So it's just a little aside, and I'll come back to the stochastic versions, but even though we've been mostly studying the deterministic case, you can generalize many of these ideas to thinking about the brain as doing probabilistic inference, in the sense of finding searching through the set of probable configurations of the neurons given the inputs. Okay. There's one bothersome thing here about using these kinds of energy functions, which you already find in Hopfield nets and Boltzmann machines, which is that it looks like you need to have symmetric weights. In other words, the synaptic strength for going from I to J should be the same as from J to I, which isn't biologically plausible. So if you strictly take the derivative, you get these weight updates which are non-local, because now the ith neuron needs to look at both the synaptic weight, of the signal coming from J, but also of the signal of the weight that links it to J. So that doesn't sound very reasonable. The reason it comes up is because if you have an energy term that links neuron I and neuron J, and you say that, well, what neurons are going to be doing is essentially going in the direction of the negative gradient of the energy, so trying to minimize the energy. And similarly, the other neuron is going to be doing the same thing, but with respect to its activity. So they're both trying to minimize the energy. And then, so if this is the direction where each of the neurons are moving, and then you look at what it means for how they change, there's going to be, and you linearize those things. So you take this, you write it as the second derivative times Sj, right? So this is a function of Sj, and so you now can think of this as a weight that multiply Sj, and you see that you get the same weight for both Si and Sj. That just comes from the fact that second derivatives are symmetric, right? So that's basically a consequence of having an energy function and assuming that the dynamics are basically going down the gradient. Of course, we don't have to make these assumptions, but the brain is probably not doing that. But there is some good news about the symmetry assumption. So the first good news is that if we have a kind of layered architecture, and each layer is forming a good autoencoder with the next layer, something that comes up repeatedly in many of the things we've studied, then you get sort of this symmetry arising for free through the learning. So the minimizing reconstruction error of these pairs of consecutive layers will yield symmetric weights, even though initially they're not symmetric. So we observed that experimentally a few years ago, where we train an autoencoder with a single hidden layer, and the weights going up and the weights going down are different, but after training, they converge to something close to being symmetric copies of each other. And this was recently proved by Sanjeev Arora in a sort of theoretical setting with some assumptions that are reasonable. Another reason to not worry too much maybe is that it looks like if the feedback weights aren't the symmetric of the feedforward weights, backprop still works. At least this is an empirical observation from the work of Lillikrap and collaborators from about 2 years ago. Now, I'm still not satisfied with all these things, and I would like to come up with learning procedures which don't rely at all on this symmetry thing. At the end of my presentation, if I have time, I'll say a few words about some current work where instead of thinking about learning an energy function, we think of learning transition operators. So what that means is basically you can think of it like we have a dynamical system that's just something, a mapping from the current state to the next state, and you can think of it as in a stochastic sense, and that's what we mean by transition operator. And so that dynamical system has parameters, and instead of trying to learn the parameters of the energy function, we can think of learning the parameters of the dynamical system itself, right? So instead of assuming that the brain is minimizing some energy function or approximately minimizing an energy function, we say, well, it computes some dynamics. How do we change the weights of the system, which directly control the dynamics, so that it does what we want? In other words, the dynamics converges to probable configurations that make sense for the data. Right, except here we're trying to learn a complicated joint distribution over a very high dimensional space, which I think is a very different thing. That's right, that's right, that's right, that's right. We're trying to directly design, well, we're trying to directly learn the dynamics. We can't really design it because it depends on we're trying to model the world, right? So, but yeah, we're learning the dynamics rather than learning an explicit energy function or probability function. Okay, but now let me start on this path to connect backprop with SCDP and so ideas of potential, how brains could potentially implement something like backprop. So I guess before I do that, let me say a few words about the use of the autoencoder constraint. So if you have a sequence of layers like this, so think of it like maybe we have inputs here and we have higher level areas here, or vice versa, and we have feedforward connections, feedback connections, and the feedforward connections and the feedback connections between two consecutive layers form a good autoencoder. What does that mean? It means that they kind of invert each other. If I put in something here, I send it through this path, and I look at how these guys are gonna, what signal they're gonna send back. If the signal sent back agrees with what was received here, then we have sort of the right conditions for autoencoders. And it turns out that if you have these kinds of conditions, then after a single feedforward pass, so you would need something that sort of shuts off the feedback connections temporarily, and you would just do the feedforward path, and then you allow the feedback path to turn on. And if this is a very good autoencoder, and they're all very good autoencoders, then you basically are already at the fixed point just after you did this. Now, of course, there may be more complications, like you have maybe other modalities coming in, and that's going to change the representations you get. But in the simple setting where you just have like one modality and you're trying to predict something, you can have a very fast convergence if the consecutive layers form autoencoders. So that's one thing that is interesting to make the idea of going to a fixed point more biologically plausible. Now, the connection between the propagation of perturbations and backprop. So this is the thing from about a year ago. And in this paper, what we do is we show mathematically that if you have one of these fixed point networks, so in other words, it's a recurrent net where we're going to clamp the input and we're going to let the dynamics run until things don't move anymore. That's a fixed point. And also we're going to have these symmetric weights. Then there's a particular condition at the fixed point, which is such that now if I'm going to perturb the fixed point by changing some of the values of some of the neurons, maybe they have inputs from other systems, and making those changes just very small changes. So we're going to introduce epsilon perturbations to these. Now, because of the feedback connections, that perturbation is going to change the values here, because these guys want to be in agreement with these guys and these guys. So now the perturbations we had here have been propagated here. So after these guys have changed a little bit because of that perturbation, of course, those guys are not going to react to the fact that these guys have changed, and they go to a slightly different place. And in the initial instance after those perturbation is introduced, the directions in which all of those guys are changing actually corresponds to the gradient of some cost, where the initial perturbations would correspond to the derivative of the cost with respect to the y's here. So if the outside world is telling those neurons how they should change slightly to be more in agreement with this cost, to minimize that cost, then the symmetric feedback connections will propagate that information in just the same way that you would expect from backprop. There are some more details behind this, but that's the idea. Okay. So, yeah, yes, you can think of the axis as the outside world, which is clamped, and the y's, you can think of something you're predicting. But you can also think of both the x's and the y's being the outside world. So you want to predict y given x, and you observe x before, and you make a prediction of y before you see it. Then you see it, and that will make you change the y's towards the correct value a little bit, and that's a perturbation that gets propagated down in this recurrent net. Okay, so now about the sort of, this was not a complete theory. It says, okay, so we have these perturbations and they propagate like backprop. It doesn't tell us that, for example, we're going to get some kind of weight update which corresponds to the gradient. So that last paper that we had a first version last February, but an update last October, really gives us a complete mathematical theory to make these kinds of connections with backprop complete. So, and this is basically the work I've done with my PhD student Benjamin Cellier. Okay, and actually we think that this theory extends beyond the potential application to neuroscience, but could be used in a more general way as a new principle for machine learning when what you want to do is think of it like train a physical system. So let's say we have a physical system, like a piece of, some solids and some liquids or whatever. I mean, something that obeys, that has a Hamiltonian, right? Anything that has an energy function, we can play with. And where the state is continuous, and the dynamics could be either deterministic or stochastic. And it has parameters, and we'd like to change those parameters to make a cost function, improved. So we want really to know how to change the parameters to make that smaller. So we want to compute dc d theta. But the relationship between the cost and the parameters is complicated because it's through the dynamics, and the dynamics could be stochastic, so it's a pretty complicated relationship. You can't just do analytically the computation of the gradient. So how are we going to do that? Well, so we're going to assume a few things about that energy function. We're going to assume that the places where the dynamics are stable, so the fixed points, correspond to zeros of the gradient of the energy with respect to the state. So if f is the energy, df ds is the direction in which the state wants to change in order to reduce the energy. And when that vector is zero, it's like either a local minimum or a local maximum. Then if there was no noise, then the system would stay there, right? So this is just the same kind of assumption we had before. And in the stochastic case, the equivalent statement is that the state, after it reaches its equilibrium, which is the equivalent of this s dot equals 0, follows a distribution which is proportional to e to the minus energy. Right? So that's like a standard Boltzmann type of distribution, except everything is continuous here. So yes, this is an assumption that the system has this property that it converges to. And physical systems will have these properties, right? So if there is an energy function, physical systems will converge to a local minimum of the energy. Or if it's stochastic, to the Boltzmann distribution. That's why I'm saying, that's the mathematical way of saying, oh, we have a physical system. There is an energy function, there's a Hamiltonian, and the system tends to sample from the states in proportion to their e to their minus energy. So this work is related to a lot of previous work to which I won't be able to give enough justice, but really this thread of thinking started in the late 80s with the work of Almeida Pineda, who proposed a way to compute gradients in recurrent networks. The problem with this approach is that, in terms of biological plausibility, is that it essentially requires a different kind of network for the feedforward path and the feedback path, and in particular, the feedback network is also a recurrent network, but it's a linearized version of the feedforward network, and that doesn't make much sense from a biological perspective. That we're going to have these two networks that share weights, and one is purely linear and the other is nonlinear. This is also related to the early work on contrastive Hebbian learning. The problem with contrastive Hebbian learning is that it's a learning rule, but it doesn't have a really clear mathematical justification. For example, there's no guarantee that it goes down with respect to some objective function. In fact, it can go, it can give rise to inconsistent updates in some senses. And that's generally a problem with handcrafted learning rules, that it's not always clear what they mean from an optimization point of view. Boltzmann machines, of course, the learning rules for Boltzmann machines do optimize something clear, but it's not clear how the two independent phases are related to backprop. We'll see how, with this work, the connection becomes more clear. And one of the algorithms for Boltzmann machines, which has been proposed, contrastive divergence, also has some theoretical issues in the sense that, again, it doesn't optimize any objective function. which doesn't mean it doesn't work. It actually works reasonably well, but it has these issues. And there's also some really interesting work from Xi and Song showing a relationship between contrastive Hebbian learning and backprop in, again, a very special case where the feedback weights are very small, epsilon small, and you have different learning rates, exponentially growing learning rates at different layers. So the approach that we are proposing seems to address essentially all of these issues, at least in theory. And the experiments we've done seem to show that they can learn deepness. Okay, so to try to be a bit more formal, we're going to have some kind of architecture. It doesn't have to be layered, actually, but the simple case we study probably is layered. So we have some inputs x and some outputs y and some hidden layers. And there is also some values of x and y in the external world. So here we're not going to force we're not always going to clamp values like we do for the Boltzmann machines on the neurons. And so we make a distinction between the internal values for those input variables and the actual value from the outside. Same thing for the y. Because we're considering the inside value, the network value, and the external value as two different things, we're going to also introduce a new concept, which is which we call influence parameters, which is how much force is being exerted by the outside world to make the inside value match the outside value. So you can think of it like how much relative current is coming from this guy compared to the other guys. And if the relative current coming from here is much larger, then essentially you're just clamping that value to that value. And those betas are controlling that strength. So beta equals 0 means the inside value is free from the outside value. Beta is infinite, it means it's clamped, and anything in between means some pressure is being put from the outside. We're also going to decompose. We don't have to do it, but it's sort of convenient to take the energy function and think of it as being broken into two kinds of terms. The kinds of terms that have to do with how neurons like each other's configuration. So that's like the internal energy, so relating pairs of neurons inside or even triples, it doesn't matter. So we have some internal energy which only depends on the state of the network, so all of these guys from the state. And some other term which involves the outside values here, which we call V for visible. And of course the beta, which controls how strong these terms will be. So for example, the internal energy could be like our Hopfield-like energy function that I showed before. And the external potential energy could be something simple like square difference between the internal value and the external value weighted by those betas. And you might have different betas for different groups of units like here. Okay, so this is just a setup. And now, in this setup, if we can compare what we are proposing to the contrastive Hebbian update because it's very close. In the contrastive Hebbian learning rule, you would essentially do a weight update proportional to the difference between two sufficient statistics, to the gradients, so two sufficient statistics, right, which is the derivative of the energy with respect to the parameters in two different states. One state would be a state where you don't clamp, and one state would be a state where you clamp. If you're trying to do supervised learning, really what we mean here is that we're always going to be clamping the inputs, but the outputs are either going to be free, where the beta corresponding to the output is 0, or the beta is going to be infinite or small. If it's infinite, then it means we're also clamping the outputs. So basically in contrastive Hebbian learning, we're going to be either clamping only the input, or we're clamping both the input and the output, and we're comparing how the neurons behave in the two phases, and that gives us the update. So in the kind of learning rule that we're proposing, which we can show is going to be a gradient with respect to a cost function, we get something similar, except that instead of fully clamping the outputs, we're only going to nudge them towards the right value, and so the beta is going to be some small value. But it's otherwise very similar. And we can show that that difference properly scaled is the gradient of a cost, say like squared error, but it doesn't have to be that, it could be any cost, with respect to the parameters. So So you could generalize this setting to any kind of architecture, doesn't have to be layered. And you can generalize this to the stochastic case. So this is again the same equation I showed with more notation. Basically it's saying, look at the, and I'm sorry if the e's have become f's and so on, I'm sorry for that. But basically we're taking again the derivative of the energy with respect to the parameters in two different states. One, in fact, is going to be very close to the other because the only thing we're going to change is we're going to change one of the betas by adding a small quantity, which corresponds to putting a little bit of pressure on say, the output units or whatever you want to, that depends on the cost. And you can turn that into a stochastic version where you just stick in some expectations here over the states under the probability distribution that, the Boltzmann distribution that these things follow. Okay, so this looks a little bit maybe heavy in notation and so on. But essentially what we're doing is, again, we have some big dynamical system. We clamp the input. We let it go to a fixed point or to whatever sample from the its stationary distribution. Then we change a little bit the energy by putting, which is going to end up putting some pressure on some of the units that we would like to be different in order to minimize a cost. And that pressure should correspond actually to the derivative of the cost we care about with respect to these units that we're going to be changing. So the outside of that network is now putting some pressure, just a little bit of pressure, and that's going to change the whole network state slightly. And now we could just compare the sufficient statistics, which are things like pre-synaptic times post-synaptic activity in the two states. And in fact, I'm going to come back to that. In fact, we can do something even more biologically plausible. But first, this is another Microsoft bug. First, let me say a few words about this SCDP connection that I mentioned before. So to turn the thing that I've been telling before into an actual weight update that's more biologically plausible, it turns out that if you make your weight change proportional to the pre-synaptic firing rate times the temporal derivative of the post-synaptic firing rate, then and then you convert the firing rates into spikes, and then you look at the temporal differences between spikes, and you draw the difference, the relationship between the spike timing difference and the weight change that occurs in average, you get a profile that looks very much like the classical SCDP observations. Now I know that SCDP is much more complicated than this picture, but it's interesting that you can recover this kind of relationship with a learning rule that doesn't really care about spikes so much as the rates and the temporal derivative of the rates. But yes. So the bottom graph is basically the same thing. On the x-axis is the minus post difference, time difference, and the y-axis is the weight change. But that's coming from our simulation using these kinds of updates. And this is, of course, from the, bow or something. Yes, we are just observing the delta spikes, right? So there are some underlying rates. So you mean understand why we get this profile? Well, yeah, in the paper we have a kind of explanation, but it has nothing to do with energy. It's just has to do with the the slope. The important thing here is the slope of the firing rate is directly correlated with the direction of change of the weights. That's the main characteristic here. We can talk about it afterwards. So in any case, if you use this energy function that I showed before, and you apply this learning rule that we derived mathematically, that gives you a gradient of the cost function, you end up that the weight update should be the difference between the pre times post in one fixed point versus pre times post in the other fixed point. We have two fixed points, right? The first one we get at and then the one we get after a perturbation. But of course, it would be kind of crazy from a biological perspective if we had to wait for very specific times to say, okay, now it's time to make a weight update. It makes much more sense if the weight update goes on continuously. So you can, if you do this kind of weight update, which is just doing all the time a weight update proportional to the temporal derivative of the product of pre times post, then you recover the thing we want, so long as you do the changes in the phase after we got the perturbation, after we got the signal from the outside. So there needs to be a kind of global synchronization signal here that says, okay, so now I'm going to give you the right answer, or now I'm going to give you some pressure towards the right answer, and you're allowed to start changing weights. But while the thing is doing pure inference, it's not supposed to be changing its weights according to this this thing. So there's an issue of, are there global synchronization signals, or maybe we can break down into smaller units. I don't know. So one potential candidate for this kind of global synchronization could be something like acetylcholine, which is distributed everywhere and has the right kind of time scale for controlling phases like, now we're receiving signals that we want to optimize over, and now we're just doing inference. So many of all of the algorithms that I showed before have this property that they have these kinds of two phases, and I think it's a very interesting biological question. Is there such a thing in brains? So we've tried this on fairly simple vanilla feedforward nets with feedbacks, of course, and we're able to train those nets to zero error on the training set of MNIST, and they get about 2%, 3% depending on the architectures test error on MNIST. So we don't really know why they're actually worse than normal feedforward nets in terms of generalization, but at least they can learn, which is the main thing. And more recently, Gerstner and his group, including Menard, who was working with me on the previous project, have taken the same rule and tested it, where instead of having like we had in our simulation just rates, right? There was no spikes in our simulation. So they basically created a spiking version of the same thing and showed that it was able to learn again. So that's, I think, interesting. Now, for those of you who are more interested in the machine learning connections, I think there's something really interesting that at least gives me an insight about what's going on here, that also helps us understand why backprop is so much more powerful than methods like reinforce or any kind of finite difference method where you have to introduce perturbations or changes to all the parameters. If you look at the update, formula, you have this difference, and what it is really is like a finite difference update. We're going to make a small change, but it's a one-dimensional scalar change, which is the amount of perturbation we're applying. And when we're dividing by the amount of perturbation, so we are estimating a gradient with respect to a very high-dimensional object, which is the parameters, by doing a finite difference perturbation in a single direction. And that single direction happens to be the direction of how to make the network agree a little bit more with the cost to reduce the prediction error. So we've turned a problem of estimating gradients, which if you were to do finite difference estimation would be humongous, because you would have to consider finite differences in all the dimensions, into a one-dimensional finite difference problem. Right? So I think that's, of course, backprop achieves this using an analytic calculation of the gradient, whereas here we're doing this, it's like a finite difference where we consider two possible values, but that's two states for the whole network, not per parameter. So it's incredibly efficient as the size of the network grows compared to these other methods which consider changing all the weights. There's one particular version of this which is kind of related to what I said about getting to a minimum in one shot. So if the energy function is something like the sum of square differences between each layer's state and what the layer below wants it to be, then if you do a single feed-forward pass, you get immediately to a global minimum, because then you set everybody to what the lower layer wants. Unfortunately, for unsupervised learning, this would be a useless energy function. But for supervised learning, of course, this is a very natural thing to do. But you probably want to add extra terms to this to make this more interesting. But still, it would mean that the initial feed-forward computation would give at least kill off all these terms of the energy function. Okay, so what's in front of us? I would really like to get rid of this symmetry constraint problem. As I mentioned, we're looking at ways to learn a transition operator for that, learn the dynamics. I want to generalize these ideas to unsupervised learning, because essentially the thing we've looked at is practical when the cost function is something computable that's tractable, like what you would get if you do classification or regression. But if the cost is a log likelihood which involves an intractable computation, like you would typically get in unsupervised learning, then this approach doesn't apply. An unrelated question, but I think very hard, and for which I think nobody has any clue, is, okay, so we've done something maybe reasonably plausible for backprop, but that's backprop in sort of static nets, or the equivalent of static nets. What about backprop through time if you have a sequence? Right, so we use backprop every day in deep learning to get the kinds of feats I showed you before. It's all using backprop through time. And it's totally unclear how brains could do something like backprop through time yet. So in the last few minutes, let me tell you about some of those directions of investigation which try to deal both with the symmetry issue and with unsupervised learning. So if you think about the kind of update that we proposed, or the SCDP-like updates, if you think a little bit about it, what you find is that really what the system is trying to do is to say that the states that we are visiting in the future are better than the states that we visited in the past, right? Because we had a prediction and then we changed the system towards a better configuration, and the weight update, the SCDP-like update, is saying, well, we want to emphasize the configurations we're going towards and de-emphasize the configurations we were before. Okay, so it's basically good at predicting the future. It's trying to predict its future states. The weights are going to change in such a way that it's going to make the system go faster towards a state that it would find later if somebody gave it the answer. And so it tends to remember the states that it visits once you clamp the Y's. Now, there's some issues, as I said, for unsupervised learning, which is that I don't think it makes sense for something like predicting the next frame of image to make a point prediction. So I think there's a lot of work in theoretical neuroscience where we take this view that maybe we're going to be predicting the next image and then using something like a regression costs, which makes sense if the conditional distribution of the next image is something that can be approximated by a unimodal distribution like a Gaussian. So in other words, if I think that given everything I know, the next frame I'm going to see is basically one typical image plus or minus some noise, then this is a good model. But it's not a realistic model. The truth is the next frame could be taken from a highly multimodal distribution. Like, for example, things may start moving left, or things may start moving right. And And so this whole approach of sort of simple pointwise prediction doesn't make any sense anymore. It doesn't make sense for the brain to compute a single configuration of what the next image coming to the retina should be. Okay, so what do we do? So one idea is if the system can't go towards where the data would be, it can't make a prediction, well, maybe we can just reverse things, right? So if we start from a data point, and then we would like to make that kind of configuration more probable, and we allow the system to move away from such configurations, then we have something that can capture multimodal distributions. This is actually what is happening in the contrastive divergence rule. So we looked at how we could implement something like this using, again, these STDP ideas, but what we find is that you would need something like a reverse STDP. You need something that prefers the past and wants to forget the future. Because if we start from a data point and the configuration, the fixed point that the data point brings you, and then we let the system move away from it, it means that the old value is a better value than the new value. So the sign of the update should be completely reversed. So if the control mechanism is in the other direction, in other words, we start with the right answer and then we let the system move away from it according to its dynamics, then the weight update should be a reverse SCDP. And so is there any instance of reverse SCDP in the brain? I don't know, but there's something natural that came to me, which is that if you had reverse SCDP, basically what would happen is you would be forgetting the states that you were just visiting. And in dreams, we have this property that like we're forgetting the dreams as they come, and when we wake up, we forget them very quickly. So maybe there is a kind of reverse SCDP going on in dreams. And it could make sense that dreams would be seeded by things we've seen during the day, and then the brain just runs its stochastic dynamics starting from these states that we sampled during the day from when we were constrained by the outside world. So we explored an algorithm that's based on these ideas that we call variational walkback, that's being submitted to ICLR. And another property of it has all the properties that I've been discussing. Another property that it has is that not only we like it, in contrastive divergence, we clamp the input, we let the system go to a fixed point given that clamp input, and then we let it go towards what it likes. Here we do the same thing, except we also increase temperature. We allow the system to be very noisy, and that actually makes the math better in the sense that we describe in the paper. But that also makes it more like dreams, right? So in dreams we have this very incoherent sequences of states that may correspond to high temperature versions of the brain dynamics. So what the role of this, according to this idea, the role of sleep would be to kill off spurious modes, because what happens is you start from data you've seen during the day, and then you explore configurations that the brain would like at high temperature, starting from this configuration. And that essentially would move towards things that the brain likes but shouldn't like, and you're trying to inhibit that. So that's something interesting to explore from a neuroscience perspective. Okay, there are other things that we're doing. This is my last slide, that try to exploit this backprop implementation that I discussed to implement another unsupervised learning algorithm that has been very, very popular in the last year, called GANs, Generative Adversarial Networks, in the machine learning community. So it's an algorithm for unsupervised learning of generative models, but the training procedure for this is using backprop. It's not supervised, it's unsupervised, but there's a training objective. And we could imagine using the kinds of machinery that I've described here for doing unsupervised learning, using a GAN-like framework, but implementing the learning using the kind of STDP fixed point thing that I mentioned today. So these are the kinds of things we're exploring right now, going towards getting rid of the symmetry constraint and generalizing these ideas to do unsupervised learning, because I think that's the main thing that the brain does, in addition to reinforcement learning, of course. All right, so I'm going to stop here and take your questions. Thank you.